All right, so today we're going to be talking about arc length and surface area. So let's say that you have a curve, and I always draw pretty much the same. It doesn't matter what the curve looks like. The idea is you have a curve. You're going to start at point A and then to a point B. So you're going to just care about the graph of a function, say from A to B. The rest doesn't matter. Oh, that's crooked. All right. So what we say, let's say f of x. What we'd be interested in is measuring the length of this curve. So if you had a little piece of wire and you could put it around it and then you could measure it down, how long would that be? And what would that be useful for? Well, if imagine you're designing some sort of application where you need a cable to go around that curve, you could then measure and then cut it and put it in. Or sometimes other applications could be useful. So let's think about how we would actually do it or how we would measure it by using calculus. So as usual, what our normal approach is we subdivide into a number of subintervals, our original interval, and then we will, in this case, let's say we're here. I want to just divide it into 4 subintervals. And you could do the following. You could just draw a straight line between the 2 points. Then here you draw a straight line, and you're going to be off by a little, but you will be getting an approximation. As you can see, even for my graph, it looks, because my lines are not perfectly straight, you can see a little bit like it's the same thing. But you're getting an approximation, and the more of these subintervals that you put, the closer your approximation will be. So what would that look like? Let's say that we're partitioning this into n subintervals, and they're uniform. They're all going to be of a delta x width. And so let's say right here, this one would be a delta yi. So for each, this would be delta y1, the height here, delta y2, the delta y3, delta y4. But in general, just call it delta yi. All right, so what would be the length of this little line? Well, you have a right triangle right there. So you have that this length is going to be just the square root of delta x squared, which is the base, or one of the sides of the right triangle, plus delta yi squared. So that's just your Pythagorean theorem right there. So if you wanted to approximate the length, and I'm debating whether to write it here, I'm going to write it here. Let's call it little l. For length, I don't know. So it'd be the sum from I equals 1 to n of this lengths, which are going to be the square root of x squared plus delta yi squared. And that would give you an approximation. Sorry. If you want exact, you're going to do a limit as n goes to infinity. So let's do an approximation there. All right. So what we can do here is we can factor a delta x out. So if I factor a delta x out of there, well, technically I got to factor a delta x squared, and I get a 1 plus, and you say, well, there's no delta x on this term, but I can write it as delta yi over delta x squared. And I can pull this one out of the square root. And here's a moment when we actually use the mean value theorem. So, because remember that whenever you have the delta yi over delta x, that's just the slope of the secant line. And what the mean value theorem is that there exists a ci somewhere in between here, where the derivative is the same as that slope, meaning the tangent line has the same slope at that point as the secant line. So we can replace that with that f prime of ci, whatever that may be. We don't care, because then we're going to take a limit and we're going to end up with an integral, as you can see now. So it's going to be f prime of ci squared. And so if we were to take a limit as n goes to infinity, what this will turn out to be is that the arc length between a and b is going to be exactly equal to the integral from a to b of this term here, square root of 1 plus the derivative of the function at x, the whole thing squared, dx. So that delta x turns into a dx. That ci, well, that's just going to be your derivative of the function. And we now have an expression. So this expression is what we're going to be using to compute the arc length. All right, now a word of warning here. Whenever you compute arc lengths, the integrals that result are very seldom going to be integrable by the methods that we currently know. So you're going to have a hard time actually finding those integrals. And a lot of the exercises will say, if you cannot find an exact value, then use a computer or a calculator to get a numerical approximation. So make sure to look at the examples and see if that's the case, because you may be breaking your head trying to compute the integral, and we simply don't have the tools to do it. And at that point, we're going to resort to numerical integration. All right, so let's go ahead and do a couple examples, but keep that in mind. Okay, so our first example will be finding the arc length of this curve, which, by the way, looks, it's not a parabola, but looks kind of like that. You can plug that into Desmos and take a look. And so that's going to be your graph, roughly. And we're looking for that length, the length of that curve there, on the interval from 0 to 1 on the x-coordinate. All right, so remember our arc length, the formula we computed a second ago, would tell us that would be the integral from 0 to 1 of the square root of 1 plus the derivative of the function. Let's call it just y prime. I'm going to do it in steps. Just want the formula at the moment. Let's compute the derivative now. So it's going to be 3/2 of x to 3/2 minus 1 is 1/2. And then we have to square it. So let's square it before we even do anything. So the square of 3/2 is going to be 9/4. And this problem is it's rigged, so it actually works out. So now I can plug that in. Oops, integral first. 1 plus 9/4 of x dx. So now this one I can integrate. There are very few functions you actually can integrate. This is one of them. And so I'm going to do a u substitution. U equals 1 plus 9/4 of x. And du would just be 9/4 of dx, from where I get that 4 9s, just multiplying times the reciprocal, of du is dx. So I can plug that in. And I get this, the integral. I'm going to do the endpoints in a second. Square root of u. And then instead of dx, 4 9s, put it in here, of du. Now we do need to do endpoints. At x equals to 0, you get that u is going to be 1 plus 9/4 times 0 is going to be 1. So this endpoint turns into a 1. At x equals to 1, which is my other endpoint, u becomes 1 plus 9/4 by plugging in here. 1 plus 9/4, which is going to be 4, plus 9, 13/4. All right, so I can change that here and put it as 13/4. Numbers may not be too pretty on this exercise, but it's okay. All right, so now I can integrate this one nicely because I have u to 1/2. I just do power rule for that one. So I do my copy my 9/4. You do 1/2 plus 1 is 3/2 over 3/2, all between 1 and 13/4. As I said, the numbers are not the best, but they're okay. So let's cancel a few things first. So the 3 and the 9 give me a 3 when I cancel. The 1/2 and a 1/4, remember this one becomes a 2 in the numerator when you multiply times the reciprocal. So the 2 and the 4 give me a 2. And this is going to be u to 3/2. Now I got to do the square root and then the cube of 13/4. That's going to be a somewhat ugly number. We're just going to leave it indicated. So that's going to be 13/4 to the 3/2. I can still do a square root of the 4 and get a 2 coming out, then cube it, get an 8, and so just get 13, something like 13 square root of 13 over 2. Sure, but we're not going to simplify it, but you could. And then 1 to the 3/2. We're going to leave it like that, just because it's not going to get much prettier. So as I said, 13 square root of 13 over 8. I said 4 before, it was 8. Minus 1. All right, so that's how you solve them, however. All right, let's do another one of these, and then we're going to move to surfaces. And the surfaces are the surface area of the solids of revolution. So you're going to grab a curve, you're going to rotate it. Instead of rotating a region, you're going to now rotate just the curve. That's going to generate an area. But we're going to get to that in a minute. We're going to do one more of these before. All right, so now I'm going to talk about one where the function is x as a function of y. What do we do? So let's draw it first, I suppose. So my interval is on the y coordinate. So it's going to be, the graph is going to look like this. So going from 0 on the y to 1. I mean, technically this one is one that is really easy, that you could just solve y as a function of x. And do it that way, but the formula works also if you do it in terms of y. So you can also do 0 to 1 square root of 1 plus x prime squared, and the prime here represents derivative with respect to y, which is kind of weird, but that's okay. And then dy. So you can change your function to be a function of y and then do a dy. Everything is the same. So let's go ahead and take our derivative with respect to y, which is weird to write at x prime, but whatever. So it's going to be 2y. And yes, there's no implicit differentiation. There's no y prime, because remember, my derivative is with respect to y. I don't like it. It's boggling my mind. In any case, that's what it is. So integral from 0 to 1, and then square root of 1 plus, oh, I forgot to take the square. Should do that. It's probably better to do the square separately, because sometimes you will have to FOIL things out. So it's better to already have it FOILed and just plugging it in. So 4y squared and then dy. And now with the tools that we currently have, we're unable to integrate this. This you can integrate whenever you do trigonometric integration or trigonometric substitution. So we'll talk about that later in the semester, but this one is one that you would approximate numerically. So we're just going to stop right there, and we're going to move on to surface areas. All right, so let's talk about surface area quickly. So let's say that you have the same curve we always draw between A and B. I draw it a little bit lower this time because I got to rotate. So we're going to draw it a little bit closer to the axis. Let's say you have your same curve I always draw, which looks like a square root, I think. So from A to B. Okay. And now what you're going to do is you're going to rotate it. But you already know that's going to take me a second, so I'm going to draw it, erase, draw, erase, draw, erase until I get it right. Then I'm going to come back to the video. All right, I didn't erase nearly as much. So when you rotate this one around, you form this kind of like a bowl kind of thing, and then a flat bottom at the end. So it's pretty much like a bowl to eat your cereal. All right, so what we're going to be doing, however, this time I am not rotating. Notice what I'm not doing. I'm not grabbing the area under the curve and rotating it where it would give me a solid. I'm just grabbing the curve itself and rotating it around, so it would make an infinitely thin surface that goes around, so it's hollow all the way. So this would not have a flat. No, it wouldn't be solid at the bottom. It'd just be a circle in the bottom. And that we're trying to compute the area of that surface that we generated. So it's not a solid, it's a surface. Before we had rotated a region, so we got a solid. Now we're just rotating a line or a curve and we're getting a surface. So this one takes a bit more work to compute. You have to do some little bit more involved calculation, but the surface area is going to be given by 2 pi area from A to B. I was going to write 0 to 1. We're doing it. We've done that so much. Then f of x, by the way, the curve was y equals f of x, and then the square root of 1 plus f prime of x squared. By the way, I failed to mention when this formula applies, and of course it applies only if you can take your derivatives, and so everything in here makes sense, and you can integrate even though numerically. So I forgot to mention that. However, the functions you're going to be given in this class are going to be such functions, so you don't have to worry about that technicality, but it's worth mentioning. So that will be our formula. Let's do just one quick example to close the video. Again, these ones will also be the kind that that you may not be able to integrate other than numerically. So don't stress if you end up with an integral that you cannot compute. If you follow the steps correctly, if you wrote your formula correctly, then you should be all right. And if you're in my class, if you're not just, if you didn't just find a video online, I will just ask you to set up the integral because of that same problem. Anyway, so let's do the example. In this case, y equals x cubed, and between 0 and 1. So let's draw it first, and then I want to move here to solve it. So remember the cube function, sort of like that. And if you're going to rotate it around, I didn't tell you around where, right? That would have been a good idea. So firstly, my labels. I was going to do the wrong one. Let's go from 0 to 1. I could have moved my 1 a little bit higher. Oh well, too late. And when I rotate around the x-axis, would have been a good idea to say that. So when you rotate around here, you get that sort of figure, and you're trying to find the surface area of that figure there. So now that we saw how it rotated, maybe we eliminate the rest of the graph, because why not? We're going to go from 0 to 1. So let's leave that there. All right, so that's what we're trying to do. All right, so just to apply the formula, notice that I have to find y prime, which is going to be 3x squared. And this is a very nice example, but you'll see why. So of course I give myself the best examples, and then I leave you to the numerical integration. That's not fair. Oh well, so let's go ahead and compute the rest over here. I'm going to erase and meet you in a second. All right, so we're going to plug into our formula. Integral from 0 to 1, 2 pi. I'll put it inside. I didn't give myself room to put it outside. Then the function, in this case x cubed, the square root of 1 plus the derivative squared, 9 x to the 4th dx. And notice that this one looks very complicated, much more complicated than the ones we had looked at before, because you have that x cubed outside. But notice that that's going to be really nice, because when you do your u substitution for this one, du will be 4 times 9, 36, x cubed dx. And notice that the x cubed dx is here. So you can just solve for that x cubed dx So write 1 over 36 du, and that's going to be your x cubed dx that you can now substitute in. I'm going to do the endpoints in a second, so let's keep going. I should have done the 2 pi outside, my bad. But this x cubed dx is going to be 1/36 of du. That is already taken care of. And now I just get the square root. I left too much room, because this is just the square root of u. And there's space there. So you see now the substitution worked out quite nicely. So at x equals 0, you get that u is equal to 1. And at x equals 1, I'm taking my old endpoints, turning them into new ones. U is equal to what? 10. So at x equals to 1, 1 times 9, 9 plus 1 plus 1, 10. All right, so from 1 to 10, and now it's just a matter of writing this as pi over 18. Now I'm going to take the compute the integral of this, which remember is going to be, it is u to 1/2. So I'm going to do u to 3/2, adding 1 to the exponent over 3/2. Evaluated from 1 to 10. And again, numbers may not be too pretty here. Now the 3 doesn't cancel, but then there's a 2 that goes to the numerator. 2 and 18 gives me a 9 times 3, 27. And then you get to evaluate, so 10 to the 3/2 minus 1 to the 3/2, so that's just minus 1. And you get your area of the surface of revolution. So the surface area of this object is going to be given by that. All right, and that, by the way, would be unit squared, so because we're computing an area. So that'll do it for this video, guys. Thank you so much, and I'll see you in the next one.